Today's lesson is on finding areas of regular polygons. You're going to have your calculator for this lesson, so please pause here and go get your calculator. Don't sit here and do this without it, even though it's just in your backpack. Go get it because you need the practice. All right, we got to remember, what is a regular polygon? Oh, all the sides are congruent and all the angles are congruent. That's what we mean by a regular polygon. And what we know is that the area of a regular polygon is related to the distance from the center of the polygon to a side of the polygon. And what would be the center of the polygon? Well, it would be the center of the circle that we could circumscribe about that polygon. So that's the center, and oh, I think that was right here. The center is the center of the circumscribed circle. So if we circumscribed a circle about a regular polygon, the center circle would be the polygon circle 2. The radius of a regular polygon is the distance from the center to a vertex. The apothem, this is probably a new word for you, the apothem of the regular polygon is the perpendicular distance from the center to the side. So you can see I've got all that labeled here in the picture. Here's my apothem. I'll draw it in red. The distance, and of course we always talk about distance being perpendicular. Perpendicular distance from the center to a side. And then of course the radius is the distance, and this is not perpendicular, distance from the center to a vertex. All right. And of course that would be the radius of the circle too. So here we go. Here's the theorem that says if you want to find the area of a regular polygon, all you got to do is find the apothem and the perimeter of the polygon, multiply them together, and half that. A equals 1/2 AP. All right, sounds simple enough, right? Well, let's do some examples. What is the area of the regular decagon? Okay, so what do we have here? What are we given? So we know a decagon has 10 sides. We know because of our theorem that we just learned, we need the apothem, but luckily they've given us the apothem. I don't really appreciate that it's a decimal, but I took this problem right out of the book, so that's what we're going to use. They give us the apothem, they give us a side length of 8 inches, so I can find my perimeter, right? The perimeter is 8 times 10, because I got 10 sides, which is 80, so the area is 1/2 AP, which is 1/2 times 12.3 times 80. And when I simplify all that, I get 492 inches, square inches. Okay? That's it. It's very simple when they give you the side length and the apothem, but as you can imagine, that won't always be the case. So let's look at what we got here. A honeycomb is made up of regular hexagonal cells. So I'm going to come over here and, well, maybe, let me see something here. Maybe I can draw a hexagon. 1, 2, 3. This is a hexagon right there. Let me see if I can do this. Okay, yeah, that didn't turn out too well. Just leave that over there. Forget about it. I'm going to try to sketch one up here. Let me try to erase that one. I can't erase it. I need this guy here to move. Okay, I got rid of it. So I'm just going to try to sketch one. It won't be perfectly regular, but it'll be good enough because I got to have a sketch, right? If you've learned one thing from me this year, I hope that it's when you want to solve a math problem, if you could possibly draw a sketch, draw a sketch. Okay, we're pretending like this is a regular hexagonal cell of the honeycomb. The length of the side is 3 millimeters. So all these side lengths are 3, 3, 3, and so forth. What is the area? Okay, let me write my formula, because remember I'm doing that every time so I don't forget. A half AP. Okay, well the perimeter is easy enough, right? I can get the perimeter. The perimeter is 3 times 6, which is 18. Yes? Okay, but what I don't have is the apothem. So I'm going to sketch my center in here. Here's my apothem, right? It's the perpendicular distance from the center to a side. And what I'm going to do here with these polygons is I'm going to create myself a little triangle, right? Because I can find the side length of a triangle because I know a whole lot about triangles. And what do I know here? I know, of course, that this is a right angle. And what I got to think about here is this angle, right? We're going to have to use some trig here unless it's a 30, 60, 90 triangle. So what if I wanted to find the measure of that angle right there? Okay, let's look at this entire triangle. We're breaking this thing down by triangles. Okay, if I draw that triangle right there, and remember now, we got a triangle, we got a circle that's circumscribed around this hexagon. So if I were to look at this whole angle here, that would be a central angle, right? That intercepted this arc down here. And what would the measure of that central angle be? Well, there'd be 6 of those, right? There'd be 6 of those triangles inside of this hexagon. If I sketched them all in, there'd be 6 congruent triangles. Yep, 6 congruent triangles, and all of those central angles there would be 360 divided by 6, which is 60 degrees, right? That would be my central angle. I'm going to go really slow on this problem. I promise we won't need to use all this time once we understand what we're doing. So the central angle, which I have highlighted here in red, central angle is 60 degrees. But remember, what I'm looking for is to find this little angle in that triangle, in the green triangle, so that it's going to be half, right? It's going to be half of that. So the angle I'm looking for, let me come out here now. This is going to be something that you want to do. You want to break your little triangle out here, so that's going to be 30 degrees. Here's A, and that's about all we, oh no, we know that if the whole side length of that big triangle that we drew there is 3, then I know that this little piece right here is 3 halves, right? 3 halves. Because if the whole side length down here, let me show you what I'm talking about. If this triangle right here, I'm going to highlight it in black now. If it's got that side right there that's 3 units long, which is what was given to me, then I know that half of it for this little triangle is going to be 3 halves. Okay, so now I got a 30, 60, 90 triangle. That means that angle has to be 60, which now tells me that my short side is 3 halves. So what is the apothem? Oh, well, I just got to multiply that by 3, right? So I'm going to come over here. I'm going to say my apothem is 3 halves times the square root of 3. Yes, because I'm taking the short side of my 30, 60, 90 triangle, multiplying it by the square root of 3. So now I've got all I need. So I know that the area is 1/2 times the apothem, which is 3 times the square root of 3 over 2, times the perimeter, which we found over here, which is 18. So let's see here. That's going to cancel with that and give me a 9. So it looks like I'm going to get 27 times the square root of 3 over 2. And that would be, what are they? Millimeters. Square millimeters. Okay, so there's my area. Now, I want to show you something really special here about the regular hexagon. So let's go back here and look at our regular hexagon. And let's look at the little triangle for a second. If I wanted to find the hypotenuse, right here, the hypotenuse of this little triangle, well, it's twice the length of the short side, right? So I'd have to multiply 3 halves by 2, which would give me 3, right? So the hypotenuse is 3. So friends, what I'm getting at here is if you take any one of these triangles inside of a regular hexagon, I'm going to draw this one now in purple so you can see what I'm telling you, because this is very, very important. So if you've zoned out right now, you better zone back in, because what I'm telling you is that this regular hexagon is made up of 6 equilateral triangles with side length of 3. So 3, so all the radii are 3 units long. I got 6 equilateral triangles in that hexagon. What did I learn in the last lesson about the area of an equilateral triangle? Square root of 3 over 4 times s squared. So if I had just known that before I did all this work over here, I would have known that the area of this regular hexagon is just 6 times the area of one of these triangles. So square root of 3 6 times the square root of 3 over 4, and my side length is 3, right? So 3 squared would be 9, and then right away I would have gotten, let's see, 2 goes into that 3, 2 goes into that 2, that's 27 times the square root of 3 over 2. So look how much easier my work would have been. So what I'm getting at here is remember that a regular hexagon is made up of 6 equilateral triangles, and the side length is the side length of the hexagon. So whenever you have to find the area of a regular hexagon, you can find the area of one of those equilateral triangles, multiply it by 6, and then you got it. You got the area of the hexagon. Okay, now we're going to use some trig. What's the area of the regular nonagon? Well, it would help if I knew what a nonagon is. 9 sides. Area equals 1/2 AP. 10. So what I'm going to do is I'm just going to come right out here and I'm going to draw my little triangle that I have to work with. And here's that triangle that I'm talking about. I'm just blowing it up. Blowing it up so I know what I got. So here's A, so here's A, here's X. What is X, guys? What is X? It's half of 10, right? If the whole side length is 10, then this little piece is 5. So now I need to figure out what the measure of this angle is right here. So how are we going to do that? We're going to find what the central angle would be in a nonagon. And what would the central angle be? Well, it would be, how many sides does it have? 360 divided by 9, which is 40 degrees. Okay, so the entire central angle, if I drew one big triangle in here, every one of those angles would be 40 degrees. But of course I'm halving that, so I shouldn't draw it. I shouldn't draw it in red because it's half. So this angle measure right here is going to be half of 40, or 20 degrees. And this is going to be the step that we have to take every time unless we have a 30, 60, 90 triangle. Okay, so now we can find the perimeter easily. The perimeter is 10 times 9. 9 sides, 10 centimeters each, 90. We got to find the apothem. Okay, let's use our trig because that's the only way we can do it. Let's see. The apothem is the side adjacent. 5 is the side opposite. So guess what? I got to use the tangent. The tangent of 20 equals side opposite over side adjacent. Therefore, the apothem is 5 divided by the tangent of 20, right? So now, here's another very important thing to note. What I do not want you to do, and you will lose points for doing this, is rounding this off to a decimal and plugging it into the formula. What you're going to do is you're going to, oh, look, I actually had it broken down by step here. So let me just fill it in this way and I got more room. So the measure of the central angle of the big triangle would be 40 degrees. So 20 degrees for the little triangle that we're working with. And the way you find the central angle is to just divide the number of sides of the polygon into 360. Okay, so we just did this up above, so we know that A is 5 divided by the tangent of 20. Okay, we found the perimeter. We know that's Nonagon 9 times 10 centimeters equals 90 centimeters. So now what we're going to do is we're going to plug all this into our formula. A equals 1/2 A. What did we decide? It's 5 divided by tan 20. Do not put a rounded off decimal in there. Times 90. So let's go to our calculator and do that. So A is 1/2. I'm just going to call 1/2 0.5. Oops. In the interest of making my work easier here. So 1/2 times A. And what have I got for A? Remember, I'm going to make a fraction, so I'm going to go alpha y equals, enter. And that's going to be 5 divided by the tangent of 20. Oops, yeah. And then I want to go out of there, close my parentheses, and our perimeter was 90. So that's how your equation needs to look. Or you could say times 1/2 instead of the 0.5. But anyway, when we put that in, we get 618, and what does it tell us? To round it to the nearest hundredth. So we're going to put 618.18 as our answer. And it's square centimeters. And that's the gist of it, guys. That's how you have to use trig to find the areas of these regular polygons. Now, there's one more little formula here for you before you just got a bunch of practice problems. So let me show you this, because you will have to use this from time to time. If you've got a triangle, any triangle, doesn't have to be a right triangle, we can find the area of a triangle by using this formula here, 1/2 times any two of the sides. In this case, they picked B and C. Any two of the sides times the sine of the angle that's in between those two sides. So I could also find the area of this triangle by saying 1/2 times, I could pick AB times the sine of C, right? That's the angle in between AB. I could do 1/2 AC times the sine of B. So any one of those three formulas would get me the area of a triangle. That doesn't have to be a right triangle. Just two of the sides and the sine of the angle in between. So here's an example. What's the area of this triangle? Well, it's 1/2 times the two side lengths, 12 times 21 times the sine of the angle in between them. And if I round that off, it's going to be approximately 93.64 square centimeters. Okay, let me see what we want to do here. I'm going to work, I think, the next one of these with you, and then I'm going to let you really put your mind to work and try to do the others. Whatever you have problem with, we'll go over it in class. So let's do this one, and then the rest are yours. A stop sign is a regular octagon, 8 sides. The stop sign has a 16.2-inch radius. What's the area? Okay, I'm not going to draw an octagon. I'm just going to draw my little triangle, and I'm going to do it over here to the side so I have more room to do my work. So regular octagon, here's my little triangle. I know I got 8 triangles in there, right? This one has a radius, there's my radius, 16.2. The radius of the polygon will always be the hypotenuse of your little regular triangle. So what's the area? Area is 1/2 AP. I'm going to write this down so I don't forget it. So let's see, here's A. Got to find this angle. How do we find this angle? We find the measure of the central angle. And that's going to be 8 into 360, which equals 45 degrees, right? But that's the entire triangle. I need half of that. So this angle right here is going to be 45 halves. And if you just have to change that to 22.5, then knock yourselves out, but I'm just going to leave it 45 halves. Okay, we're going to call this x because we need to know that to know the perimeter, right? We know the perimeter is going to be 8 times x. So what we're going to do is we're just going to solve this little right triangle, and then we can punch it into our formula there. Okay, so here we go. So the apothem. So once again, no, this time, look, I got the hypotenuse, so it looks like I'm going to use sine and cosine. So the apothem would be the side adjacent, so that's cosine. So the cosine of 45 halves degrees is A over 16.2, right? Therefore, A is 16.2 cosine 45 halves. Yes? And that tells me that x would be 16.2 times the sine of 45 halves. So what I'm going to do now is I'm going to take these two things. I've found everything I need. I'm going to plug it into my formula here. 1/2 A is 16.2 times the cosine of 45 halves. And the perimeter is 8, right? Look, perimeter is 8 times x, so 8 times 16.2 sine of 45 halves. I can just hear my friend Levi right now. Oh my gosh. Yeah, but that's what it is. You're not going to round any of these values off before you get to the final answer, because there's just too much error that comes in the rounding. Okay, so let's go over here. I'll show you how to do it with your calculator one more time. The rest of the time tonight you're on your own. So what do we got? We got, and once again I'm going to use 0.5 instead of a half. It's just a little bit easier. So I'm going to multiply that by 16.2 times cosine of 45 halves. Cosine, I'm going to put my little fraction in here. 45 divided by 2. Close that parentheses. And then, what did I have? 8. Let me go back here just a second. Let me go back here and look at my picture. The parentheses, hold on. Hey, guess what? I hope somebody already found it. I made an error right here. Right here. What is the perimeter actually going to be, my friends? Somebody who knew this. It's not going to be 8 times x. It's going to be 16 times x. How come? Because this little piece x right here, it's only half the length of one side of my octagon. So, oops, this should be 16. Whew, I'm glad I caught that. I would have been off by a factor of 2. Thank goodness. All right, let's go back now to our calculator. Where were we? So we got that much in. Now we're going to multiply that by 16 because now we're getting the perimeter. And once again, that's going to be times 16.2 times the sine of, need a fraction here, 45 halves. And you might be using 22.5. That's fine. I'm sure you like that better, especially Matt Brenningmeyer. So go ahead and do that if you want to. So wow, I think that's it. Now what's going to happen, guys, when I hit my enter button, if I get an error, it's probably because I messed up with my parentheses. Let's see if I did. Oh no, I don't think I did. What I got is 742.29. What did they ask me to round to? the nearest square inch. The nearest square inch. So I'm just going to say the area here is approximately 742 square inches. So, hey, somebody Google that and see if that really is about the size of a standard stop sign. I don't know where I found this problem, but I hope it's realistic. Okay, now, this has already been a long lesson. My apologies. I want you to pause here, and I want you to dedicate yourselves to working these problems before you get to class next time. I'm going to put the answers up. We'll go over whichever ones, even if it's all of them, we'll go over the ones that you need help with. But you must try these before you come to class. Okay, I'm going to pause, I'm going to write the answers, and then you work them and come back and check. All right, so our practice problem started off with a hexagon, which we love because we know that a hexagon is made up of 6 equilateral triangles. So I just used my formula, found the area of one triangle, multiplied it by 6, and I got 96 times the square root of 3 square units. Would you get the same thing if you used a half AP? Yes, you would. Okay, next one. We got a regular pentagon. So I broke out my little triangle that I'm going to use here. I can see that 12 is the radius because it's the distance from the center to a vertex. So remember, I always know that is the hypotenuse of my little triangle I'm working with. So I know when I've got the radius, which is the hypotenuse, I got to use sine and cosine, which is what I did here to get my apothem and perimeter. And when I punch all that into my calculator, that's what I come up with. Put a star on it if you got a question. Okay, here's a good one. I got to find the area of the shaded region. Oh, how am I going to do that? Well, I'm going to find the area of the big hexagon and the area of the little hexagon, and I'm going to subtract out the area of the small one, which is what I did here. And you see I got 162 times the square root of 3 square feet. Don't need to use trig because it's a hexagon, and I got 6 equilateral triangles in there. Okay, and finally, the Pentagon in Arlington has side lengths of about 921 feet. What is the area? So I broke out my little triangle. I know if the entire side length of the Pentagon is 921, then this little half, of course, is 921 halves, and I'm going to leave it that way. Again, if you want to change it to a decimal, knock yourself out. And so I had to use tangent because I've got the side opposite and side adjacent. So I got this complex fraction for my apothem. I know my perimeter because I know the side length, 5 times 921, but I'm just going to put that right into my formula over here, 1/2 AP, and when I punch all that in, I get that answer right there. If you need me to show you how to do any of these, give you any help, let me know. Help you with your calculator, let me know. But that's all we got on the area of regular polygons.